to add my little personal word.
All right, everybody, we are live. So, plan for today looks like this. First, joker quiz. I want to finish up the star sheet on the types of reactions. We got a little bit into it on Wednesday. We'll review that quickly. Then we'll go over the parts that we didn't get to on Wednesday. Because of how far we got and how far we didn't get on Wednesday during block day, I revised the calendar a little bit. Reactions got moved from Thursday to Friday. Acids and bases stuff got moved to Monday, and then reaction rates got moved to Tuesday. Okay? Your next quiz will be on your next block day, which for you guys is Wednesday, over reaction types and rates. So just a quick review of what we're doing there, what types of reactions do we have out there, et cetera, et cetera, et cetera. Next Wednesday, we're back on lab with like chemicals and fire and everything, okay, over types of chemical reactions, okay. But just a reminder, that lab is the lab that you will write your formal lab report on for this grading period. On Friday of next week, I'll give you time in class to work on your lab report. Okay. One thing I think I mentioned to just some of you guys, maybe not all of you, I reserved time in the library for us to work on this thing, but third period was booked. So we do not have library time. But it's, working on writing up your document and things like that. So if you have a laptop or if you want your iPad, whatever, if you want to bring it in on Friday so you can work on it during class, I'm okay with that. If not, you guys can just talk and write some things down and then transfer it to, type it in over the weekend or whatever. Okay? Lab report will be due the following Tuesday. So Valentine's Day lab report doesn't get any better than that.
Are you doing anything else?
So
I'm just grateful. We have an awesome Valentine's Day party every week of Valentine's Day. Well, that's it.
My son told me actually that Monday is their 100th day of school. Like the 100th day of school celebration.
Yeah.
So
We like
Our teachers would make sausages and give us 2 donuts and say one.
very nice.
Really?
But anyway, your lab report is due the Tuesday after lab, so you'll have time in class to work on it Friday. If you want to work on it over the weekend, if you have questions, you can email me or talk to me on Monday, and then lab report will be due on Tuesday of the following week.
Can we all bring in Valentine's?
If you want to bring in Valentine's. So that is our plan for the next week and a half. All right. Let's go back to types of chemical reactions. On Wednesday, we talked about the idea that the last unit in chemistry deals with chemical reactions and how matter changes from one form to another. We said on Wednesday that if we look at all of the chemical reactions that are out there in nature, they all basically fit into 5 categories, and those are represented by the 5 points on the star of your note sheet that I gave you on Wednesday. We talked a little bit, why do we categorize things? What's the advantage to looking at a big group of information and trying to put it into categories? Awesome. What's one thing?
It's more organized.
It's more organized. We're trying to find something that would be good too, right? What's another reason why we categorize things? What's the advantage to trying to narrow down the information that we're looking at? Awesome.
To find like what the substance is?
Yes, kind of. You're getting at it sort of in a roundabout way, right? We did it. You guys remember the activity that we did the one day where I had the list of foods all up on the board and we put them into categories? And we talked about certain categories were better than other categories, right? What do we put things in categories for? Nick?
You can kind of start predicting properties and finding similarities between things.
Good. Especially if we don't know about something that's in a category. If we know about other things that are in that category, we can make some predictions about what that unknown thing might be. And that's what we do with the types of reactions as well. So, one type of reaction we talked about on Wednesday was a combustion reaction. And we said that there's a requirement for something to be a combustion reaction. What is that requirement?
Just as it has to have oxygen as its reactant.
Has to have oxygen as one of its reactants. O2 by
And
itself.
that to not combine with anything else.
Say again?
Not combined with anything else.
Well, it has to combine with something else.
Well, I meant like plus O2. Like that's
Right.
what I see.
Right. It has to be O2 by itself. Yeah. Okay. We talked about that this reaction, one that we talked about quite a bit over the past couple of days. This fits the bill as a combustion reaction. Yes. One of the ones that was on your quiz. What about that one? Does that fit the bill as a combustion reaction?
Yeah.
It does, right? These are both combustion reactions. On Wednesday, we talked about a specific kind of combustion reaction. Okay? And that was combustion reaction that takes place with hydrocarbons. Does that sound familiar? So we talked about that there is a class of chemicals out there that we refer to as hydrocarbons. Why? Because they consist of carbon and hydrogen. And when those hydrocarbons go through combustion reactions, a reaction where O2 is one of the reactants, right? They form two specific products. Remember what the two specific products were?
Water and carbon dioxide.
Water and carbon dioxide. That's not to say that the product of every combustion reaction will be carbon dioxide and water, but every combustion reaction with a hydrocarbon will be carbon dioxide and water. Here are two examples of combustion reactions where the products aren't carbon dioxide and water. Good? Get on those things? Okay. Is that as far as we got, or did we get to the next one?
We got the synthesis.
Okay, we got synthesis. All right. So, the next type of reaction we talk about is a synthesis reaction. Because you know English, right? When we synthesize something, what are we doing? Producing it. We're making it, right? And a synthesis reaction is a reaction like that, where we're taking something small, right, and making something more complex. One of the products is more complex than any of the reactants that are out there. Represented, right, by the puzzle. Okay, we're taking small pieces of the puzzle, putting them together to make something big. Does that make sense? Here are a couple examples of synthesis reactions. First, this is something called the Haber process. You don't need to know that. But this is producing something we call ammonia. We take nitrogen, N2, we mix it together with hydrogen, H2, and we produce this compound, NH3. This was one of the reactions that was in your packet on Wednesday that you had to balance. Okay? A synthesis reaction, because what are we doing in this case? Taking small things and making them bigger. Okay? This one keeps showing up, right? Maybe.
Hey, this is YouTube.
That's right, man. This is out there on the web. There we go. All right. So, this one keeps showing up. We've already said that this is a combustion reaction because it has oxygen as one of its reactants, right? We already said that this is a combustion reaction because it has oxygen as one of its reactants. But what else are we doing in this process? Taking two small things and putting them together to make something big. So this is a combustion reaction, but it's also a synthesis reaction. So some reactions can be classified as two things, although we'll find that really only combustion and synthesis are the only two combinations that we can really put together. Okay? Once again, this one on the bottom. Does it look familiar? It's on your quiz. Okay, there's the balanced equation for that.
That was the answer.
Reaction number one. So, but
I'm pretty sure I got that one.
also, this fits into two categories as well, right? It is a synthesis reaction because we're taking small things together and putting them together to make something big, but it's also what? It's also a combustion reaction because it has O2 as one of the reactants. Good there? Synthesis reaction. The general form for a synthesis reaction looks something like this, right? So we take A plus B, and we make together AB. Take substance A, substance B, join them together, we make substance AB. Right? That's what we're looking for in terms of a synthesis reaction. Questions? Good there? Okay.
Can you ever make like more? Could it ever be like AB or A plus B equals like AB plus something else?
That's something different. We'll get into that in a second. Yeah, Caroline, generally in a synthesis reaction, we're going to end up with one product. We're taking small things together, making them into one bigger thing. Next type of reaction we talk about is a decomposition reaction. Once again, because you know English, you probably can figure out what goes on in a decomposition reaction, right? What happens in a decomposition reaction?
Taking big things and break it down to
Taking big things and breaking them down into smaller things. Just like the puzzle pieces down here in the bottom right-hand corner. Right? So reactant is broken down into two or more simpler substances.
So the other side.
Yep, that's going to be the right-hand side of the star. That's going to be your decomposition reaction. Okay? As far as the general form goes, right, we look for something like this. A, B starting together, breaking down into A plus B separately. There is a picture of pop, because pop is an example of a decomposition reaction. I'll show you in just a second.
Oh, yeah.
As far as examples go, the bottom one is something, sorry, it's pretty dumb though. But, I think most of you guys saw this last year. Did you guys see the electrolysis of water?
Yeah.
I got that impression that most of you have seen it. If you pass electricity through a sample of water, it will break up into hydrogen and oxygen. That is a decomposition reaction. Does it happen on its own? Will water break down into hydrogen and oxygen by itself? No, you have to add energy to it, in this case in the form of electricity, but you still end up with, you start with one big thing and you end up with two smaller things. The one right above it, Sam, you mentioned, right, there's a picture of pop there, okay? Pop is this substance on the left. It's the reactant compound, H2CO3, which we refer to as carbonic acid, okay? Yes, pop is an acid. Okay, yeah, it does, doesn't it? Okay. Pop is an acid, right? But under certain conditions, pop will exist in the H2CO3 form. But if you change the conditions, this reaction will go from left to right, and it will break down into two smaller compounds. What are the condition changes that you have to make in order to make it break down?
Temperature?
Temperature could do it, although not quite as good as another one. Yes, in one form. What do you have to change? You have to change the pressure. How do you change the pressure in a bottle of pop? Open it. Okay? When you open pop, what happens to it? It fizzes, right? Because that change in pressure causes this decomposition reaction to happen. What's one of the products of this decomposition reaction? CO2. What's that? Carbon dioxide. What form does that look like in your pop? That's bubbles. Okay? So, yes sir.
Why does the bubble open?
So, say again?
Like, why does it, like, after you shake it up and open it, why does it go like
So you're adding more energy to it, right? You're shaking it increases the energy, and that energy causes the breakdown of this compound into these. So you make more CO2. More CO2 means more what? Means more gas, more bubbles, and that's what happens, right? If we let this reaction go all of the way, and we break down all of the carbonic acid into these things, right? What happens to all the bubbles eventually? They go away, and you're left with what? Water. Except it's not water, it's what? It's flavored water. We refer to it as flat pop, right? Flat pop is just this reaction where all the CO2 has gone away, right? Does that make sense? Decomposition. Yes, Allison?
Would you ask us like break it apart?
No, not at this point, Allison. Especially like in your quiz next week, it'll be more, hey, what kind of a reaction is this? Okay, what kind of reaction is this? That we get into that more in chemistry and honors chemistry, where if you have this type of compound, once again back to the categories thing, certain types of decomposition reactions happen with certain types of reactant compounds. So these ones break down a certain way, blah, 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 but that's more of an honors chemistry thing, not this class. Okay. All right, next. Single replacements. As its name suggests, we have an element that replaces another element in a compound. On your star sheet, that's the bottom left point of the star, a single replacement reaction. If we look at the general form for a single replacement reaction, it looks something like this. So we start with A plus BC. What is the A representing when it's by itself? It could be oxygen, or more generally, it's just going to be what? One kind of atom, let's say. So it's a what? An element. Okay? BC, that's going to be a compound of some kind. It's two elements joined together. Not necessarily boron and carbon, but just in general, element B and element C. But if we look, if we follow along, right, what happens? It's not necessarily, Allison, that it splits apart, but what does A do?
Wow.
It goes in and it kicks B out of that compound and it forms its own compound. Right? This is a single replacement reaction. Single replacement reactions are kind of easy to spot because what are you going to see on the reactant side? What did we say this represents? An element and a compound on the reactant side, and then on the product side, it's going to be an element and a compound. Something kind of like this. Okay? AgNO3, silver nitrate. That's a compound. Right? Plus copper. That's an element. The copper goes in and kicks out the silver out of that compound and forms its own compound with nitrate and leaves silver there by itself. Okay. That make sense? Okay. The bottom one, we're seeing the same thing, except which part of the compound is being replaced in the bottom reaction? The anion part, right? In the top reaction, the cation is being replaced. Silver and copper are both metals. They're cations. The one metal goes out and kicks out the other metal. But here, right, the bottom reaction, chlorine's a nonmetal, iodine's a nonmetal. Where's chlorine going to go? Is it going to kick the potassium out of that formula? No, it's going to take the place of the iodine. Right? This picture over here on the right shows the first reaction, the silver nitrate and the copper. You might not be able to see, but if you look, there's a clear liquid in the test tube, and there's a copper wire that gets just lowered into it. Okay? Eventually, what do you see happens to the copper wire? It gets all like fuzzy, right? And I don't know, you might not be able to tell depending on the projection or not, but what happens to the solution in the test tube? It turns blue,
Different chemicals.
right? Say again?
Different chemicals coming out of the copper.
Right. It's not algae. Nick, what's one of the products of this reaction? The top one here.
The coil becoming fuzzy, and then the water.
What is the fuzziness? What's one of the products of this reaction?
Silver.
That's silver. The fuzziness that shows up on the outside of that copper wire is the silver that copper has kicked out of its original compound. Okay? How do I know? Well, it doesn't look like copper, right? Okay? But also, the blue solution inside the test tube, blue solutions are what copper things do when they're dissolved in water. So the fact that the solution went from clear to blue means that now the copper is dissolved in the water. Whereas the silver was dissolved in the water, it was all clear. Now this fuzziness that's on the wire is the silver that was just left there by itself. Okay? Kirsten, go ahead.
So is it like water with silver in it?
Basically, you have water with silver and nitrate. This is a solution, but the copper doesn't react with the water, it reacts with the silver and the nitrate to kick the silver out, leave it all fuzzy here on the side, and forms a compound with the nitrate. That's the blue tint that you see in the test tube. Okay? Megan, good.
Yeah, why nitrate?
that has more to do with the refraction of the light. But if you talk about like what's the blue gem? Sapphire's blue. Is that Sapphire's blue? I can't. Sapphire, emerald, emerald green, right? Rubies are red. Okay. So, garnet. Isn't garnet purple?
Oh, God, it's red.
It's rubies or
Amethyst is purple. Anyway, but Megan, something that's blue like a sapphire has copper in it. The water being blue is more of the way that light reflects off of the water, so that's a little bit different. But things that are blue generally have some kind of a copper. It can be blue or green, but depending on the type of copper that you put in. So, but that's a little bit different. Chris, go ahead.
So is the Planisek stuff just pure silver?
Yep.
So we didn't try selling that.
Technically, you could, but it's really not that much. I mean, it's a test tube, like you're not really making that much. But
Do enough.
that is a way that you could, that is a way you could make silver.
Okay.
All right, we go with silver replacement.
Can we try that?
Yeah, you'll do it actually in lab next week.
We're doing mass.
As long as the
No. It takes like a whole no. Actually, you guys don't do this one. I think honors chem. You do this in honors chem. I'm pretty sure.
Could you get to
Can we
keep
do
the
it?
silver?
You don't get to keep this.
how long will it
Why not?
Does the school sell it for money?
No, the school does not sell it for money.
That's more fun than it is.
Could you away in
It's a really small amount of silver.
Let's see.
All right. Actually, if silver toilet seed, that'd probably be so good. Water, silver reacts with water, kind of like furnaces,
I get like a huge copper.
All right.
So it'd be like a really
Come on, one more. We're almost there. We're almost there.
So it's like you had a big
Top, quick and tiny, under a tiny.
head here.
All right. The last type of reaction we talked about is called a double replacement reaction. In a double replacement reaction, we talk about two elements that are in different compounds that will exchange places. So whereas a single replacement reaction, you look for an element in a compound in the reactants and a different element in a different compound in the products, what are we looking for in a double replacement reaction? What are we going to see?
Different.
Two atoms trading place.
Right.
Trading place.
Two compounds in the reactants and then two compounds in the products. Right? As far as the general form goes, AB, a compound, plus CD, a different compound, forms AD plus CB. Notice, where was A at the beginning? It's at the beginning. And where is C at the beginning? Beginning, right? A and C representing cations, right? Cations are still going to be cations, and anions are still going to be anions. So we either trade the front or the back of that reaction, okay? So if we look here, right, look at the top one, potassium iodide, potassium being the cation, iodines being anion. Lead nitrate, lead being the cation and nitrate being the anion. If we come over to the other side, right, notice the lead was joined together with the nitrate, but in the product side, what's lead joined together with now?
PB.
Lead is the PB. What is it joined? It's joined together with the iodine, right? The fronts and the backs have switched. Okay? This is actually a pretty cool reaction. The top one, the potassium iodide with lead nitrate, that's a cool reaction that you will see in lab on Wednesday of next week. So see.
Big boom, fuzziness, and smoke.
We're gonna try to do that.
You look bad.
All right. Are we good here?
I'll just sign it.
Yes, sir.
Where's like the 8 before?
Yep.
Silver diamond.
Oh, okay.
Yes.
Because the two cations can't be together.
Right, the two cations aren't going to join together, and the two anions aren't going to join together. Yeah, so we look for, Elsie, we're looking for just trading cations or trading anions. All right, one thing before we kick off. Come on. Yeah, I have like 2 minutes. I have a clock in the back of the room. I can tell the time.
Diamonds,
Wow. I want diamonds.
So, up on the board, homework for the weekend, okay? There's some pages to read from the book. There's also some questions from the book. In addition to those questions from the book, on Tuesday, the problem set that I gave you, where you had to balance the equations. On the back of that sheet, there is this side that says classifying reaction types. It's also balancing equations practice, but on the side, there is a place for you to classify those reactions. Are they single replacement, double replacement, synthesis, combustion, decomposition? Answers to this are posted online. On Friday's date on the calendar, right? Where it says problems and answers. That's where you'll find the answer. Okay? Monday, we talked about acids and bases. Acids and bases.
Oh, I did that.